this tends to cool the Earth. So now we have a positive feedback loop and a negative feedback loop. Okay? One tends to amplify the effect, one tends to attenuate the effect. And the climate is full of these. There's so many feedback loops that we don't understand them all. The sum of all these feedback loops is called climate sensitivity. This is a very, very important concept. But once again, all of these feedback loops that we either understand or don't understand, they all algebraically sum together to form climate sensitivity. So that a certain amount of CO2 that is added to the atmosphere will undergo all of these different feedback loops. They'll all sum together and it will cause some kind of a climate sensitivity, which is measured by how much the Earth heats. Okay? And I might add that there are feedback loops within feedback loops. Okay? So within this feedback loop, there could be a whole mess of other feedback loops. And we just don't understand a lot of them. We don't understand them all. And if we're trying to model the system, in order to accurately model a system like this, we have to understand all these feedback loops, otherwise the models aren't accurate. And you'll see that IPCC models do not do very well. They don't do very well because we simply don't understand all these feedback loops, and we don't understand the climate sensitivity. So, here's the question. Does doubling of CO2, this is what climatologists like to talk about with their models. They like to force the models, okay? The model's in equilibrium, so they force it. They plug the numbers into the model and say, we're going to double the CO2 concentration, and that forcing, what will that do to the heat of the Earth? In other words, what will that amount be? And so, if we say, what does a doubling of CO2 emissions cost? Will it cost a 0.5% per century increase? Well, this would be calculated if there were absolutely no feedbacks in the system. That would be like example A, right? Where A causes B. Right, that would be about a 0.5% per century increase. Now the IPCC says it's going to be more like 6 degrees centigrade per century. These are predicted by the IPCC models, and they're using a lot of climate sensitivity. Okay, the only way to do that is to have high climate sensitivity to CO2. Or, how about this answer? We don't know. I like this answer, right? We don't know all of these feedbacks, so I pretend that we do. Climate sensitivity is the crux of the scientific global warming debate. And this is what climatologists stand around and talk about when they talk about science. I mean, we tend to talk about the crux of the scientific debate is whether or not CO2 causes global warming, whether or not we should pay for the money to mitigate it and all that. And those are fine extra arguments, but the climatology basically is this. The debate among scientists is what is the sensitivity of the Earth? Okay? If it's a high sensitivity, then very small amounts of carbon dioxide will cause huge changes in carbon dioxide, huge changes in temperature. If it's low sensitivity, then very large amounts of carbon dioxide will have very minimal changes in carbon dioxide. In temperature. So here's the IPCC report. The part that you haven't read about in the New York Times. It came out of the third IPCC report, which came out, I believe, in 1997. And it says, and this is really important to read. This is buried, by the way. This didn't make it out into the summary for policymakers, by the way, but it's buried in there. It says, in sum, a strategy must recognize what is possible. In climate research and modeling, we should recognize that we are dealing with a coupled nonlinear chaotic system, and therefore that the long-term prediction of future climate states is not possible. So that big group of IPCC scientists, the good guys, right, before they were edited to death, they recognize that we don't understand all of these feedback loops. We don't understand the climate sensitivities. Therefore, we have a system here which is more akin to a Rube Goldberg model, right? This is a guy here, he's changing the CO2, he's forcing the CO2 with one hand, and out pops the temperature over here. These are all the feedback loops, they're positive, they're negative, and blah, 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 and we just don't understand what's going on. And the IPCC recognized that, okay? You don't hear about this. Now here's the atmospheric CO2 that is attributable to man. I mean, the actual carbon, the actual amount of anthropogenic greenhouse effect that is caused by man is 0.12% of the total. So we have to say that if such a small amount of CO2 has such a big effect on temperature, then the climate sensitivity must be huge. Okay, this is the only conclusion that we can draw, right? Lots and lots of positive feedbacks. These models are assuming lots and lots of positive feedbacks. Ladies and gentlemen, I can tell you, as a scientist, as a person that works in biology and in medicine, and also has seen lots of natural science, that the universe doesn't put together that way. There are very few positive feedback loops in systems. When there's a positive feedback loop, that is definitely nested and protected by lots of negative feedback loops to control it. Okay? And you can see why. If we had positive feedback loops, things would just go crazy. We had small amounts of CO2, we would just cook ourselves, right? But this just doesn't happen. It's just not reasonable to assume that there are lots of positive feedback loops that create such a high sensitivity in the atmosphere. We don't see it in biological systems, we don't see it in other physical systems, we don't see it in chemical systems. There's no reason, therefore, to believe that it's going to occur in climatic systems. So let's look at some data, right? Let's look at lots of temperature data. We're talking about global warming, we want to know what happens with temperature, right? How do we measure temperature? You ever think about that? How do you measure the temperature of the globe? You stick a big thermometer into the Grand Canyon and see what happens? Well, that doesn't work too well. There are lots of ways to do it. One of them is you can determine by looking at surface temperatures from surface stations. Okay? People, there are weather bureaus all over the country, all over Europe, all over China. They all have their thermometer and they go out there every day and they measure the temperature, the high and the low, they report it, they send it to somebody, right? And so you can collect all that data and you can measure the temperature of the globe. There are even reporting stations in Antarctica. Okay? So this is one way to do it. The problem is that temperature data like this will only go back to about 1880, because before that we didn't have a lot of thermometers, right? A lot of people stick their thermometers out the window and measure them. So we have to use some other methods if we want to go beyond 1880. Another good way is to use what are called radiosondes. Those are weather balloons. We're all familiar with that. They've been around since the 1940s. We send up a big balloon and it has some very primitive equipment on there that measures the atmospheric pressure, which will determine how high it is. It has a thermistor probe on it, which will tell you what the temperature is. And it has a radio transmitter, which beams it right back down to a ground station, which records the data. Now this gives us very, very good data. We still use it today. Because the best way to actually measure temperature is to get, not the temperature of the ground, which can be full of artifacts, which we'll talk about later, but the temperature a little bit above the ground. Okay, what's called the mid to lower troposphere. About the area where jet planes fly. That's the optimum area to measure temperature. Now, what if we want to measure temperature a little bit faster? We can do this with satellites. We now have satellites that circle the Earth and can cover all sorts of ground. They can use infrared and microwave radiation as probes around, and they can actually sense temperature at the mid to low troposphere level. They can actually bounce these probes right off the sea surface and measure sea surface temperatures. And they cover a lot of ground in a hurry, so we collected an awful lot of data. This is also a very good way to measure global temperatures. Another way, say, well, what if we want to go back to, before 1880, we want to look at temperature trends from a long, long time ago. We have to use what are called proxy data. Proxy data, a branch of study called paleoclimatology. And we use this by drilling ice cores in the ice, by boreholes in the ground. And what we're doing is we're looking for fossilized algae and small animals that have died. And what we're doing basically is when we drill a core, either through the ice in Antarctica, we pull that core back out. We have maybe a half a mile or a mile of core. And the cores the sections that are close to the top represent new snowfall, right, or new ground, and that's going to represent the new atmosphere. And what we do is we take and we melt that ice in a chamber that's a vacuum, and that the atmosphere, when the snow falls and packs onto the ice, it traps the atmosphere with it. Okay, so we've got basically a sample of the atmosphere. So when we melt the ice, the atmosphere then is liberated, and we can measure the gas. We measure CO2 in there, find out how much CO2 was actually in that atmosphere. We can also measure the temperature. Say, well, how do you measure the temperature in an ice core? Well, there's a process called O18 analysis. O18 is a stable isotope of oxygen. We come to find out that oxygen 18, the ratio of oxygen 18 to oxygen 16, which is the normal isotope, it changes when the temperature changes. Okay. So the math behind this is a little bit complicated, but basically, when the O18 to O16 ratio changes, that's a good indicator, a good proxy for temperature. So now that we have, we take this large core of either dirt or ice, and we slice it up like a bologna slicer, and the farther we slice down, the deeper down in time we go, right? So if you go a mile